Imagine trying to build anything, a house, a car, even like a simple toy, without understanding how the pieces actually fit together. It would just be chaos, wouldn't it?
Well, it's kind of what chemistry would be like if we didn't understand how atoms connect.
And that connection, that's the puzzle we're diving into today. Welcome to the deep dive. We're looking into the fundamentals of chemical bonding, drawing from Chemistry, Atoms First by Burge and Overby, and some related lecture materials too.
Yeah, our mission today is really to unpack how atoms stick together.
Yeah.
Molecules, compounds, all that stuff. The goal is for you, listening, to get a clearer picture of why chemicals act the way they do. We'll even touch on drawing these structures yourself. We'll cover the basics like the octet rule, but also the exceptions and how we measure that electron pull between atoms.
Exactly. And we'll look at why some bonds are super strong and short, while others are, well, longer and maybe weaker, and what that means for stability. It should give you a really solid framework for understanding, the basic architecture of matter. All right, let's jump right in. The octet rule. This feels like the starting point for everything, right? Remind us about Lewis dot. Symbols, they show the valence electrons, yeah, the outer ones.
That's spot on. Lewis dots show those valence electrons, the ones on the outside, doing all the heavy lifting and bonding. And the octet rule, well, it essentially says atoms want that stable electron setup like the noble gases have. They're very unreactive, those noble gases. So for most atoms, that means getting, losing, or sharing electrons until they have 8 valence electrons. Hydrogen's the exception. It aims for 2, like helium.
Okay, 8 is the magic number, usually.
Usually, yeah. And a key thing here, something students sometimes get confused about, is that it's only the valence electrons, the inner core electrons. They just sit there.
Right. So if atoms are doing this gain, lose, share thing to get stable,
Right.
how do we, draw that? How do we visualize it?
Good question. That's where Lewis structures come in. They're like our molecular blueprints for covalent bonds where electrons are shared. Shared pairs are shown as 2 dots, or more often, just a single line between atoms. One line equals 2 shared electrons, and the electrons not shared, we call those lone pairs. They're shown as dots just sitting on their specific atom.
Can you give an example?
Sure. Take F2, the fluorine molecule. There's one line, a single bond between the 2 F atoms. And then each fluorine also has 3 pairs of dots around it. Those are its lone pairs. Or water, H2O. Oxygen's in the middle. It has 2 single bonds, 1 to each hydrogen. And the oxygen atom itself also has 2 lone pairs left over. Hydrogen has none, and its only electron is in the bond.
Okay, that makes sense. It maps out where the electrons are. But what if they share more than one pair? Things get more intense. Multiple bonds.
Ah, yes. Multiple bonds. That's where things get really interesting. Atoms can share more than one pair. You have single bonds, 1 shared pair. Then double bonds, 2 shared pairs, think CO2, carbon dioxide, and even triple bonds, 3 shared pairs. Nitrogen gas, N2 is the classic example. Very strong bond.
And these multiple bonds, it's not just about counting electrons, is it? What's the real impact?
The impact is huge, fundamentally. Multiple bonds, doubles, and triples are always shorter and stronger than single bonds between the same 2 atoms. Seems a bit weird, maybe. More electrons meaning shorter distance. But packing them in tight strengthens the connection. Think about that N2 triple bond again. It's incredibly short and takes a massive amount of energy, like 941 kilojoules per mole to break.
Wow, okay. So shorter and stronger.
Definitely. And that strength dictates a lot about reactivity. That N2 bond is so strong, nitrogen gas is pretty unreactive normally. Makes sense, right? It's hard to break that bond.
Right. So atoms follow rules like the octet rule. They form bonds of different strengths. But what about the sharing itself? Is it always fair? That's electronegativity, isn't it?
Exactly. Electronegativity. Imagine that shared pair of electrons, and a bond is like a rope in a tug of war between the 2 atoms. Electronegativity is just a measure of how strongly an atom pulls on those shared electrons. It's crucial because it determines how evenly or unevenly those electrons are shared.
And there are trends on the periodic table for this.
Oh, absolutely. Generally, electronegativity increases as you go from left to right across a period. Atoms get greedier for electrons, and it decreases as you go down a group. Atoms get bigger, the nucleus has less pull on those outer bonding electrons. So fluorine, up in the top right, it's the champion, the most electronegative common element.
Okay, quick clarification needed here because this sounds a bit like electron affinity. What's the difference? I know students mix these up.
That's a really common point of confusion, you're right. They both involve electron attraction, but here's the key difference. Electron affinity is about an isolated atom in the gas phase grabbing an extra electron to become an ion. Electronegativity is about an atom's pull on electrons. It's already sharing within a chemical bond. One's about gaining a whole new electron, the other's about tugging on shared ones.
Got it. So isolated atom versus atom in a bond makes sense. So this electronegativity tug of war, it creates a whole range of bond types, not just like purely shared or purely taken.
Precisely. It's a spectrum, a continuum, not black and white. At one end, if the pool is equal, or very nearly equal, you get a pure covalent bond, like an H2 or Cl2. The electronegativity difference is tiny, less than about 0.5. Electrons shared perfectly. Then, if one atom pulls noticeably harder, the sharing becomes unequal. That's a polar covalent bond. You get partial charges, a bit negative, delta minus, and
Yeah.
spider on the atom pulling harder, a bit positive, delta plus to plus on the other. Think H dash hydrogen fluoride. The difference is usually between 0.5 and 2.0.
Okay, so shared, but unfairly. And the other extreme.
The other extreme is when the difference is really big, typically 2.0 or more. One atom pulls so strongly it essentially takes the electron. That's an ionic bond. You don't have sharing anymore. You have full positive and negative ions formed, like in sodium fluoride, NaF.
And you mentioned we can actually visualize this with electron density maps.
Yes, those maps are great. They often use color. Red usually means high electron density, lots of negative charge hanging out there. Blue means low electron density, more positive character. You can literally see the electron cloud being pulled towards the more electronegative atom in polar bonds.
That's cool, visual confirmation. But can we put numbers on this polarity? Quantify the pull?
We absolutely can. We use something called the dipole moment, symbolized by the Greek letter mu, u. Think of it as measuring the separation of charge in the bond. It depends on how big the partial charges are, Q, and how far apart they are, the bond length. Q, AR. Take HF again. It has a measurable dipole moment about 1.82 Debye units, or D. Using the known bond length, we can calculate those partial charges. Turns out to be about plus 0.41 on the hydrogen and Nashku 0.41 on the fluorine.
Okay, so the numbers confirm it's not a full +1 and -1 charge, it's partial.
Exactly. It proves it's unequal sharing, not a complete transfer like in an ionic bond. The charges are always less than 1 for polar covalent bonds.
Which brings us to another concept, right? Percent ionic character. What does that tell us?
Percent ionic character is another way to look at that continuum. It compares the measured dipole moment of a bond to the dipole moment you'd expect if it were 100% ionic if the electron was fully transferred. Let's take HI, hydrogen iodide. Its measured dipole moment is 0.44 D. If it were purely ionic, we'd calculate a much larger dipole moment, around 7.73 D.
Yeah.
So the percent ionic character is 0.44773 at 100%, which is only about 5.7%.
So even though iodine is more electronegative than hydrogen, the bond is still overwhelmingly covalent in character.
Exactly. It just reinforces that idea. There's no sharp dividing line.
Yeah.
It's a smooth transition from pure covalent through polar covalent, getting gradually more ionic character until you reach truly ionic bonds.
Okay, this is all great groundwork. We know about octets, bonds, polarity, but how do we actually sit down and draw these Lewis structures correctly? It seems like there's a process you really need to follow.
There absolutely is. It's systematic, and trying to skip steps is, well, usually where frustration comes in for students. We can break it down into maybe 3 main phases.
Okay, let's hear them. Phase 1.
Phase 1, electron inventory. First, you absolutely must sum up all the valence electrons from all the atoms in the molecular ion. Remember, for ions, add electrons for negative charges, subtract for positive charges. Let's use chlorate, ClO3, as an example. Chlorine has 7 valence, each oxygen has 6, so 3 times 6 is 18. Plus 1 more for the negative charge. 7 plus 18 plus 1 equals 26 valence electrons total. That's your budget.
Got it. Count everything up. Phase 2.
Phase 2, the skeleton crew. Draw the basic framework. Put the least electronegative atom in the center. Big exception. Hydrogen is always terminal, never central. Fluorine is also usually terminal. Then connect all the outer atoms to the central one with single bonds. Just draw lines. And crucially, subtract 2 electrons from your total budget for each single bond you just drew.
Okay, skeleton built, electrons subtracted. What's phase 3?
Phase 3, finishing touches and quality control. Now you distribute the remaining electrons. Start by completing the octets of the terminal atoms first. Give them lone pairs, dots, until they each have 8 electrons around them, or 2 for hydrogen. If you still have electrons left over after that, put them on the central atom as lone pairs. Now check. Does the central atom have an octet? If yes, great. If not.
If not, what then?
If the central atom is short, you need to form multiple bonds. Take a lone pair from one of the terminal atoms and move it to become a shared pair, forming a double bond between that terminal atom and the central one. Keep doing this, maybe forming another double bond or even a triple bond until the central atom does have its octet. Carbon disulfide, CS2, is a good example where you need to form two double bonds to satisfy the central carbon.
And after all that, what are the final checks? The absolute must-dos.
Two critical checks. First, recount your electrons. Does the final structure use exactly the number you started with in phase 1? If not, something went wrong. Second, and this is super important for judging stability, calculate formal charges for every atom in your structure.
Okay, formal charges. Tell us more. How do they help us pick the best structure if maybe we could draw it differently?
Formal charge is like electron bookkeeping. It helps us decide which Lewis structure is the most plausible or stable arrangement. The calculation is valence electrons, the atom broad, minus all its non-bonding electrons, the lone pair dots, minus half of its bonding electrons, so one for each bond line. For molecules, the best structure is usually the one where formal charges are closest to zero on all atoms. All zeros is ideal. You must have non-zero charges, keep them small, like +1 or -1, and this is vital. Negative formal charges should be on the more electronegative atoms, and positive charges on the less electronegative ones.
Can you give an example of how that helps?
Sure, formaldehyde, CH2O, you could try drawing it with oxygen in the middle, but if you calculate thermal charges, you'd find oxygen gets a positive charge. Oxygen is very electronegative. It doesn't want a positive formal charge. The correct structure has carbon in the middle. When you calculate formal charges for that arrangement, everything comes out to zero. That tells you it's the much more stable, much more plausible structure.
That makes a lot of sense. Use formal charge as a reality check. But what if formal charges look okay on a few different drawings? What if even the best circle structure feels incomplete? Is that resonance?
That is exactly resonance. Sometimes a single Lewis structure, even the best one according to formal charges, just can't fully represent the actual molecule. So the resonance structure is one of two or more Lewis structures that are equally valid ways to draw the molecule. They have the same atoms connected in the same way, but they differ only in where the electrons, usually double, triple bonds and lone pairs, are placed. We draw that special double-headed arrow between them to show their resonance structures.
And the big warning here, the molecule isn't actually switching back and forth between these drawings, is it?
No, that's the #1 misconception. It's not flipping or oscillating. The real molecule is a resonance hybrid, a single stable structure that's like an average or blend of all the contributing resonance structures. Think of a rhinoceros again. It's described as having traits of a unicorn and a griffin, maybe, but it's not flickering between being a unicorn and a griffin. It's always just a rhinoceros, a unique thing. The resonance structures are like attempts to describe it using simpler pictures.
Okay, so the reality is the blend. What are some common examples where we absolutely need resonance?
Ozone, O3 is a classic. The carbonate ion, CO32, is another. Benzene, C6H6, is probably the most famous. If you draw benzene with alternating single and double bonds, you'd expect two different bond lengths. But experimentally, all 6 carbon bonds are exactly the same length, 140 picometers. That length is shorter than a single CC bond, but longer than a double CC bond. It proves the electrons are delocalized, smeared out over the whole ring. It's a hybrid. Sulfur trioxide, SO3, also has resonance 3 structures where the double bond moves around the 3 oxygens.
Wow. Okay, so octet rule, Lewis structures, formal charges, resonance, feels like a solid toolkit. But you mentioned exceptions. The octet rule isn't always the rule.
Yeah, just when you think you've got it, chemistry throws curveballs. The octet rule works beautifully for second-period elements, carbon, nitrogen, oxygen, fluorine.
Yeah.
But beyond that, yes, there are important exceptions. 3 main categories.
Okay, let's break down these rule breakers. Category 1.
Category 1, incomplete octets. The central atom simply has fewer than 8 valence electrons. This usually happens with elements in group 2 or 13, like beryllium or boron. For example, in pH2, beryllium only forms 2 bonds, so it only has 4 electrons around it. In BF3, boron forms 3 bonds, so it only has 6 electrons. There just aren't enough electrons to give them an octet using normal covalent bonds.
But boron, can it sometimes get an octet? I remember something about coordinate covalent bonds.
You're absolutely right to bring that up. BF3, with its incomplete octet, is electron deficient. It acts as a Lewis acid, an electron pair acceptor. It can accept a lone pair from a Lewis base, like the nitrogen and ammonia, NH3. When that happens, the nitrogen donates both electrons to form the bond with boron. That special bond is called a coordinate covalent bond, or dative bond. And yes, through that interaction, boron does achieve its octet. So incomplete octets often lead to specific kinds of reactivity.
Okay, interesting. So category 2 of exceptions.
Category 2, odd numbers of electrons. If a molecule has an odd total number of valence electrons, It's impossible for every atom to satisfy the octet rule because electrons come in pairs. These molecules are called free radicals. They have at least one unpaired electron. Examples include chlorine dioxide, ClO2, it has 19 valence electrons, and nitric oxide, NO, with 11. That unpaired electron makes radicals generally very reactive.
Reactive, okay. Makes sense. And the final category, the really weird one.
The expanded octet. This is where an atom has more than 8 valence electrons around it. This is only possible for elements in the third period and beyond, like phosphorus, sulfur, chlorine, bromine, xenon, etc. Why? Because these larger atoms have emptied orbitals in their valence shell that can actually participate in bonding, allowing them to accommodate extra electron pairs. Sulfur hexafluoride, SF6, is a prime example. Sulfur has 12 electrons around its 6 bonds, no lone pairs. Arsenic pentafluoride, SF5, 10 electrons around as. Xenon tetrafluoride, SCF4, 12 electrons around S for others.
So only period 3 and below can do this expansion.
Correct. Elements in the second period C, N, OF never expand their octets. They simply don't have accessible d orbitals. That's a hard and fast rule.
Now, for these expanded octet cases, like with sulfur, sometimes you could draw it obeying the octet rule, maybe with lots of formal charges, or expand the octet to minimize formal charges. Which way do we go?
That's a great question, and honestly, sometimes it depends on the level of chemistry you're studying. Often the structure that minimizes formal charges, even if it means expanding the octet for an atom that can expand, is considered the better representation of the bonding. So in something like sulfuric acid or even SO3 we mentioned earlier, structures where sulfur has more than 8 electrons but 0 formal charge are often preferred over structures obeying the octet rule but having formal charges. But the key takeaway for general chemistry is recognizing that expansion is possible for period 3+ elements and how it relates to minimizing formal charge.
Okay, what a fantastic tour. We've gone from the basic idea of atoms wanting stability through drawing bonds, dealing with unequal sharing, resonance hybrids, and even when the rules get broken. It really shows how these concepts build up.
It really does. And understanding these fundamentals, the electron tug-of-war and electronegativity,
Right.
why multiple bonds are strong, why the octet rule works most of the time, but has those key exceptions, it's incredibly powerful stuff. It lets us predict how molecules will look, how they might react. It's the foundation for understanding, well, pretty much all of chemistry and material science.
Absolutely. Think about it. These tiny connections, these rules and exceptions dictate everything. The properties of water, the strength of steel, the way medicines work in your body. So here's a thought to leave you with. Next time you look at any substance around you, maybe even the air you're breathing with all that stable N2, consider the silent, intricate dance of electrons forming those bonds. What unseen connections are shaping the world you experience?